Welcome to AI Podcast. I'm Evan, and today we're digging into HYDRA, a domain-independent agent architecture for adaptive autonomous agents from AAAI 2025.
HYDRA. Love the name. Quick headline first, what's the point of this thing?
The TLDR is simple. HYDRA is an agent that notices when the world stops matching its expectations, figures out what changed, and then fixes its own world model or reprioritizes its tasks so it can keep working without starting from scratch.
So instead of retraining a whole policy, it patches its understanding of the world and keeps going, right?
Exactly. Think of it like a self-tuning GPS. If a road suddenly closes, the map updates and you reroute. You don't throw away the car.
Nice. Who's behind it?
The work is led by Shiwali Mohan with collaborators including Roni. It's a joint effort across industry and academia.
All right, let's set the stage. What's the problem in the field that HYDRA is answering?
Most agents assume the world is stable, but real deployments are open worlds. Rules change, objects appear, physics shift. Model-free systems usually need tons of new data to adapt, and classic planners fail because their symbolic models go out of date. HYDRA tackles that gap by making novelty detection and model repair a first-class part of the agent.
When you say novelty, what counts? A new object? A changed rule? A surprise gust of wind?
All of the above. HYDRA treats novelty as anything that makes predictions and observations disagree. That could be a new entity, a parameter shift like heavier objects, or a structural change like a new interaction.
Okay, so how does HYDRA know something changed? Agents don't have sixth sense.
They use monitors. 3 basic signals. First, unknown objects, which is like seeing something you never modeled. Second, plan inconsistency, meaning your plan predicted one outcome, but your sensors report another. Third, reward divergence, when performance suddenly drops in ways that your model can't explain.
And once the alarm bells ring, what happens?
HYDRA has 2 halves. The base agent is a planner that uses a symbolic model, specifically a planning language called PDDL+, which can handle both discrete actions and continuous processes like gravity. Wrapped around that is a meta-reasoner that runs the monitors, decides if a novelty is real, and then accommodates it.
Accommodates it how?
2 main ways. One is model repair. The agent edits parts of its own symbolic model, like tweaking a parameter or adding a missing condition. The other is task reprioritization. If the world shifted in a way that makes the current plan order bad, it changes the order of sub-goals to recover performance.
So it's like a pilot who notices turbulence. First, they adjust their mental model of the air they're flying through, and if needed, they change the sequence of maneuvers.
That's a great analogy.
I'm curious about the symbolic piece. Why PDDL+, and why not just learn end-to-end?
2 reasons. First, sample efficiency. If you already have a structured model, you can localize what changed and repair only that part instead of relearning everything. Second, interpretability. A changed gravity constant or a new precondition is something a human can inspect and audit.
Right, and that matters in safety-critical settings. What did they test this on?
3 very different domains to show generality. A physics-controlled task like cart pull, but with richer dynamics. A puzzle environment similar to Angry Birds where you shoot birds into structures, and a Minecraft-like crafting world where the agent jumps around on a pogo stick and interacts with objects.
That's a fun spread. What kinds of surprises did they throw at the agent?
Things like increasing the mass so the pole swings differently, adding wind or moving platforms that change how shots land, or introducing new objects that affect crafting and movement. The idea was to cover parameter tweaks, new entities, and new interactions.
How did HYDRA stack up against the usual suspects?
Against static planners and model-free baselines, HYDRA adapted faster and with fewer interactions after a change. It didn't need wholesale retraining. And because repairs are explicit, you could see what changed, like the system deciding gravity is effectively stronger and adjusting its model accordingly.
That interpretability piece is underrated. If an agent says, hey, I think the world got heavier, you can sanity check that. If a black box just stops working and then slowly relearns, you're in the dark.
Exactly, and the system recovers during execution, not offline. It keeps trying to accomplish its goals while it repairs itself.
Let me push on detection. How do they avoid false alarms? Sometimes a plan fails for boring reasons.
Good point. The monitors rely on thresholds tuned per domain. One misstep doesn't trigger a full repair. The system looks for consistent mismatches between predicted and observed traces, and it cross-checks monitors. Unknown object plus plan inconsistency is a stronger signal than either alone.
Got it. Talk me through the model repair. Are we talking brute force search?
It's a heuristic search over a space of plausible edits, guided by the mismatch signals. They define repairable parts of the model up front, like parameters or preconditions that can be adjusted. Then they try candidate repairs, see if predictions realign with observations, and accept the ones that restore consistency and performance.
So the repair space is bounded. You're not letting the agent scribble all over its blueprint, just tweak the knobs it's allowed to touch.
Exactly. That's how they keep it tractable and safe.
And task reprioritization? How smart is that part?
In the paper, it's intentionally simple, basically rotating or reordering sub-goals when the old order fails under novelty. It's more of a proof of concept to show that strategy changes can help even without perfect model edits.
All right, strengths are clear. Where are the cracks?
First, the evaluation assumes a single novelty that appears and then persists. That's a clean test bed, but real worlds can have multiple or overlapping novelties or changes that come and go. Second, some of the repairability still depends on manual scaffolding, like choosing which parameters are allowed to change. Third, two of the domains are relatively clean in terms of observability and noise. Extending to noisy sensors and non-deterministic effects will be harder.
And a quick note on planning languages. PDDL Plus gives you nice expressiveness for continuous processes, but if you model too much detail, you can run into tractability issues. So engineering the right abstraction is part of the art.
Exactly, there's a balance between realism and solvability.
What about reproducibility? Can people pick this up and run with it?
The paper lays out the architecture and the experiments clearly, but full end-to-end replication needs the whole pipeline, from perception to ontology to planning and repair. The big opportunity is packaging it with open benchmarks for evolving worlds.
Let's ground this with a concrete example. Say we're in that Angry Birds style domain and a crosswind appears mid-tournament. What does HYDRA do?
The base planner expects shots to arc a certain way. After a few launches, the plan inconsistency monitor notices the bird is drifting sideways relative to the model's predicted trajectory. The reward monitor sees the drop in scoring. The meta reasoner proposes a repair, like introducing a win process or adjusting an implicit parameter that shifts the arc. If a quick model tweak restores prediction accuracy, the planner reuses it immediately. If the tweak doesn't fully recover performance, the agent also changes shot order, prioritizing angles or targets less sensitive to wind.
So it doesn't need 1,000 new episodes to relearn how to shoot. It updates its world story and moves on.
Right, that's the value proposition.
Let's talk authorship and venue briefly. This isn't a garage project. It's coming out of AAAI, and you mentioned Shiwali Mohan and Roni as key folks. That gives it both rigor and cross-domain perspective.
Yep, and the framing is very much about open worlds, not just toy demos.
Where does this leave practitioners? If I'm building a warehouse robot or a monitoring agent, what's the takeaway?
Carry a model you can edit. Put detectors around your plan act loop that tell you when your model is wrong. And when something breaks, try repairing the model and reshuffling your task before you consider expensive retraining.
And be thoughtful about what's allowed to change. Give the agent safe knobs to turn, like physical parameters or clear preconditions, and keep the rest locked down.
Exactly. Also, log those changes. If your agent believes gravity just got stronger, you want a trace explaining why.
What would you like to see next?
Automatic selection of what to repair, not just a hand-picked list. Better novelty signals that learn thresholds and handle noise, and handling multiple overlapping novelties with some memory so the agent can juggle several changes at once.
I'd add smarter strategy changes. Reprioritization could be value-aware, not just a blind rotation, and of course shared benchmarks for open-world adaptation, so we can compare approaches apples to apples.
Couldn't agree more.
All right, let's land this plane. Quick takeaway?
HYDRA shows that when the world shifts under your feet, you don't have to start over. Detect the mismatch, explain it in your model, and keep moving.
And do it in a way humans can read and trust. That's the difference between a brittle demo and a resilient system.
This has been AI Podcast. I'm Evan.
I'm Mia. Thanks for listening, and we'll see you next time.